The story of the John Deere 4020 often begins with admiration. Farmers across the United States saw it as a symbol of endurance, a machine capable of transforming long hours in the field into real productivity. It represented a leap forward in engineering, a tractor that promised efficiency, durability, and a new standard of comfort. Yet behind this respected reputation existed a sequence of factory flaws that countless owners only discovered the hard way. These issues were rarely visible at first sight, but once they appeared, they revealed vulnerabilities that contradicted the tractor's legend of perfection. Before we explore the first hidden defect, let me ask you for something important. We are a small channel, and we genuinely need your support to keep producing deep historical and technical documentaries like this one. Please subscribe, leave your like, and share this video with a friend who loves agricultural machinery. Your support truly helps the channel grow, and every new subscriber makes a huge difference for us. When farmers first placed the John Deere 4020 into service, few imagined that one of its most serious weaknesses was already forming inside the fuel system. It was subtle, it was gradual, and for many owners, it remained invisible until the damage was irreversible. The factory design of the injection system created conditions that encouraged cavitation, tiny vapor bubbles forming within the diesel flow. As these microscopic pockets collapsed under pressure, they produced a destructive effect that slowly damaged internal components of the injection pump. This phenomenon was not immediately recognized by many technicians. They observed irregular idling, fluctuations in engine response, or unexpected drops in power, but they often blamed low-quality fuel or poor maintenance. In reality, the issue was rooted in the original engineering layout. The relationship between the pump's internal tolerances and the vibration pattern of the engine created the perfect environment for cavitation. Every working hour expanded the problem, even if the tractor appeared to run normally on the surface. The consequences grew progressively worse. Cavitation led to premature wear on internal pump parts, including plungers and metering mechanisms responsible for delivering consistent fuel quantities. As these elements deteriorated, the fuel delivery became uneven. Operators noticed difficult cold starts and subtle but persistent power loss during heavy loads. Some reported that the engine required more throttle than usual to maintain performance, while others described a delayed response in acceleration that had never been present when the tractor was new. Another critical detail was heat buildup. As worn-out elements inside the pump struggled to maintain proper fuel delivery, the system worked harder, resulting in elevated temperatures. This additional heat further accelerated wear, creating a cycle that could destroy an injection pump long before its expected lifespan. Many pumps failed after fewer than a few thousand hours, something that astonished farmers used to the long durability of John Deere fuel systems. Repairing this defect was not simple. Mechanics often replaced worn components, recalibrated the pump, or adjusted timing, but the core design issue remained untouched. Even after a rebuild, cavitation returned because the tractor's original engineering did not prevent it. It required specialized updates and redesigns that only became widespread years later, after countless owners had already suffered expensive breakdowns. This flaw represented more than a mechanical inconvenience. It challenged the belief that the 4020 was nearly indestructible. It reminded farmers that even iconic machines had weak points hidden deep within their systems, ready to reveal themselves only after prolonged use. The fuel system defect became one of the earliest signs that the tractor's engineering brilliance was not as absolute as many had been led to believe. Among the many promises attached to the John Deere 4020, few were as attractive to farmers as the idea of a smooth, agile transmission capable of handling constant field work without hesitation. The synchro-range gearbox was introduced as a sophisticated evolution, allowing operators to shift between gears with better control and reduced effort. For many, it symbolized modernity, a system designed to raise comfort and mechanical reliability to a higher level. But embedded within this gearbox was a factory defect that quietly emerged across the nation, surprising even the mechanics who believed they had seen every kind of transmission failure possible. The first symptoms did not appear suddenly. They grew gradually, often beginning with something most operators dismissed as insignificant, a faint hesitation when shifting under load, or a momentary grinding sensation as the lever engaged a new position. At first, owners believed this came from driver inexperience, heavy implements, or minor misalignment of linkages. Yet these early signs were the mechanical equivalent of a warning, one that many only understood when the system deteriorated further. The root of the problem lay within the synchronization mechanism itself. The synchro-range transmission relied on synchronizer discs and locking elements that needed to align with high precision. In theory, this system allowed seamless shifting between certain gear ranges while the tractor remained in motion. In practice, however, the synchronizers inside the 4020 suffered from premature wear due to a factory flaw in material selection and heat treatment. This vulnerability meant that the contact surfaces inside the synchronizers degraded far faster than expected. With each shift, microscopic particles detached from the discs, gradually reducing their ability to match rotational speeds between shafts. As the surfaces became increasingly worn, the gearbox demanded greater force from the operator. Many farmers reported that what once shifted with minimal resistance eventually required strength and patience, a clear sign something deeper was wrong. The degraded synchronizers also generated metal debris that circulated within the gearbox oil. Although the lubrication system was designed to trap contaminants, it was never engineered to handle a continuous stream of metallic particles produced by premature wear. Over time, this contamination affected bearings, gear teeth, and selector rails, expanding the original defect into a wider mechanical vulnerability that demanded extensive repairs. One of the most troubling aspects was unpredictability. Some tractors experienced synchronization failure after fewer than a few hundred hours, while others lasted thousands before the issue became severe. This inconsistency made diagnosis complicated. Mechanics often disagreed on the source of the problem. Some blamed clutch linkage misadjustments, others suggested heavy loads or inexperienced drivers. But even careful operators who followed every guideline eventually faced the same grinding engagement and the same stubborn resistance on the gear lever. Field work intensified the defect. When pulling large implements or operating on uneven terrain, the gearbox faced continuous stress that magnified the synchronizer's weakness. Many owners tried compensating by changing oil more frequently or adjusting shifting techniques, but these efforts rarely prevented the inevitable. Once the synchronizers lost their integrity, gear engagement became imprecise, and the tractor developed a dangerous tendency to slip out of gear during high-load conditions. This not only reduced productivity but also created serious safety concerns during transport or field operation. Rebuilding the synchro-range transmission was costly and complicated. Replacement synchronizers installed during repairs often wore out prematurely as well, because the original manufacturing flaw remained present. It required later generation updates and redesigned components to truly stabilize the system, improvements that many early owners never received. This defect left a lasting impression on farmers who otherwise praised the 4020. It reminded them that advanced features were not immune to fundamental engineering errors. The transmission, meant to be a symbol of progress, became one of the clearest examples of how a celebrated machine could struggle with a weakness hidden deep within its mechanical heart. The hydraulic system of the John Deere 4020 was advertised as one of its greatest strengths. It promised consistent pressure, fast response, and enough capability to handle demanding implements that earlier tractors struggled to lift or control. For many farmers, this hydraulic power became central to the machine's appeal. Yet beneath the surface of this engineering pride existed a chronic defect that steadily revealed itself through overheating, internal leakage, and unpredictable performance that frustrated owners across the country. To understand the issue, it is necessary to look closely at how the closed-center hydraulic system functioned. Unlike open-center systems common in earlier tractors, the closed-center layout on the 4020 maintained constant pressure, allowing instantaneous hydraulic action whenever the operator activated a control. While this design offered superior efficiency on paper, it also introduced vulnerabilities when certain components experienced even minor wear or misalignment. The slightest internal leakage intensified system workload, forcing the pump to compensate continuously. This compensation became the root of chronic overheating. The first signs often appeared after long hours of operation. Farmers noticed the hydraulic reservoir reaching temperatures far above normal levels. Implements that previously responded quickly began to lag. Hitch movements felt sluggish, and loaders occasionally hesitated before lifting. Many owners assumed the system simply needed fresh oil, but oil changes rarely solved the problem. The true cause was a combination of factory-related valve tolerances and pump characteristics that magnified internal leakage over time. Inside the selective control valves, SCVs, small clearances regulated how fluid moved between high-pressure chambers. When these clearances were manufactured at the edges of acceptable tolerance, the valves allowed microscopic bypassing of fluid even when fully closed. This bypassing did not cause immediate failure, but it increased the system load. The hydraulic pump attempted to maintain full pressure, working harder than intended, generating heat as a natural result of its constant effort. As temperatures rose, the oil thinned, reducing its capacity to lubricate and protect delicate components. This accelerated wear inside the pump and the SCVs, intensifying leakage. The cycle repeated itself, worsening until operators faced substantial performance losses. Some farmers reported that after several hours of continuous operation, hydraulic lifting capability diminished dramatically, an unmistakable symptom of overheating. Others noticed the power steering becoming unexpectedly heavy, revealing how the hydraulic defect reached beyond implements and affected basic tractor control. One of the most misunderstood aspects of this problem was how silently it developed. There were no catastrophic failures, no sudden breakdowns. Instead, the system deteriorated gradually, almost politely, as if waiting for the right moment to reveal the full extent of its weakness. Mechanics often struggled to diagnose the root cause. Pressure checks sometimes appeared normal, and leakage tests did not always capture the microscopic internal losses occurring inside the valve assemblies. The problem became particularly evident in operations involving heavy or continuous hydraulic demand. Running a loader through repeated cycles, powering hydraulic motors, or lifting large implements placed the system under stress that intensified the defect. Farmers working in warm climates experienced overheating even earlier, particularly during intense summer seasons when ambient temperatures added to the system's internal heat load. As the defect progressed, some tractors developed characteristic symptoms: frequent pump whine, delayed hitch response, drifting of hydraulic cylinders, and unpredictable steering assist. But because each symptom mirrored those of unrelated hydraulic issues, many owners replaced hoses, seals, or valves unnecessarily. The underlying factory flaw, valve clearances and system sensitivity, often remained unaddressed. True corrections required redesigned valve components with improved tolerances, updated pump designs, and in some cases, modifications to increase overall cooling capacity. These improvements appeared gradually across later production years and service bulletins. Yet, early owners faced the consequences long before these solutions became widely available. The hydraulic defect became one of the most persistent frustrations associated with the 4020. For a tractor built to deliver power with precision, overheating and leakage represented a contradiction, a reminder that even the most advanced systems can falter when small engineering decisions accumulate into chronic mechanical problems. When owners spoke about the John Deere 4020, they often praised its engine strength, its steady hydraulics, and its dependable chassis. Yet one of the tractor's most persistent vulnerabilities was not mechanical in the traditional sense. It was hidden within the wires that carried electrical signals and power throughout the machine. The electrical harness, though simple compared to modern equipment, contained a factory weakness that revealed itself slowly and unpredictably, causing frustration that even experienced mechanics struggled to diagnose. The issue began with the materials used in the harness insulation. At the time of production, manufacturers across the industry relied on insulation compounds that performed well under ideal conditions but degraded more rapidly under heat, vibration, and exposure to agricultural chemicals. In the 4020, the routing of the harness placed several critical segments near components that produced steady warmth during operation. This proximity led to gradual hardening of the insulation, followed by cracking. Once cracked, the wires inside became vulnerable to moisture intrusion and oxidation. The first symptoms were subtle. Lights flickered. Gauges behaved unpredictably. Charging performance varied between normal and weak without an obvious pattern. Farmers reported that the tractor started perfectly one morning and struggled the next, as if the electrical system changed its behavior overnight. These irregularities were not random, they were the natural consequence of deteriorating wire insulation and the resulting instability in electrical continuity. As oxidation spread across exposed copper, resistance increased in several circuits. Higher resistance caused voltage drops under load, making systems that relied on stable power, starting, lighting, and instrumentation behave inconsistently. Some owners replaced batteries again and again, believing they were faulty. Others suspected the alternator, leading to unnecessary repairs. But even new components failed to solve the underlying problem when the wiring was compromised from within. A particularly troubling aspect was how the defect affected the ignition system on tractors equipped with gasoline or LP engines. Voltage instability altered spark strength and timing precision, creating erratic engine responses that mimicked fuel problems. Mechanics spent countless hours checking carburetors, filters, and fuel lines before discovering that inadequate voltage was the true culprit. The harness made diagnosing these issues a challenge because defects often appeared intermittently. A tractor might run smoothly for several days before the problem resurfaced, disappearing again when the wires shifted with vibration or temperature changes. Another consequence involved the charging circuit. Voltage irregularities meant the alternator sometimes failed to receive proper excitation, causing it to undercharge or overcharge unpredictably. Undercharging drained batteries prematurely. Overcharging damaged them, leaving owners confused about why fresh batteries failed within months. The gauge cluster occasionally displayed misleading information, further complicating the search for the root cause. The structural design of the harness routing also contributed to premature wear. Certain sections passed through tight corners or near moving components. Vibration caused these wires to rub lightly against metal surfaces. Over hundreds of operating hours, the abrasion removed insulation layers, exposing conductors to potential short circuits. Farmers who experienced sudden gauge failure or unexplained fuse blows often traced the problem to these hidden contact points after extensive inspection. Moisture intrusion made the situation even worse. Agricultural environments exposed tractors to humidity, rain, fertilizers, and chemicals. Once insulation cracked, moisture traveled along the copper strands, accelerating oxidation and enlarging voltage losses. The corrosion acted irregularly, creating symptoms that emerged and disappeared according to weather, workload, or even the tractor's operating temperature. Repairing the issue was not straightforward. Replacing individual wires rarely solved the full extent of the problem, because degradation tended to spread throughout the harness over time. Many tractors required complete harness replacement to restore electrical reliability, a costly and time-consuming process that few owners anticipated when they purchased the machine new. This defect became one of the most underestimated weaknesses of the 4020. While mechanical components such as transmissions and hydraulics revealed their flaws visibly and noisily, the electrical harness failed quietly and deceptively. It challenged even the most skilled technicians and reminded farmers that durability is not only about steel, gears, and horsepower, it also depends on the integrity of the small, fragile wires that bring a machine to life. The John Deere 4020 earned its reputation as a powerful workhorse long before its factory defects became widely known. Its rear axle was expected to endure heavy loads, steep inclines, and hours of continuous operation without complaint. Farmers depended on this part of the tractor more than any other structural component, because it carried not only the machine's weight but also the force transmitted from implements, trailers, and the soil itself. Yet few owners imagined that one of the most significant weaknesses of the 4020 lay deep inside this critical assembly. The rear axle bearings, responsible for stabilizing the axle shafts and ensuring smooth rotation, were installed with the expectation of long service life. But early production units revealed a surprise that engineers initially struggled to explain. The bearings wore out far sooner than the industry standard. Some farmers reported failures after fewer than a few thousand operating hours, a number shockingly low for a tractor intended to outlast generations. The problem became evident when operators noticed excessive play in the axle, uneven tire wear, or a distinct wandering sensation when driving at transport speeds. The root cause was not misuse or inadequate maintenance, but a structural mismatch between the bearing load capacity and the torque generated by the 4020's engine. Although the tractor was celebrated for its strong power output, this torque transmitted through the axle created forces that exceeded what the housing design could comfortably distribute. As a result, stress accumulated at specific points within the axle housing, areas where microscopic flexing occurred each time the tractor pulled a heavy load or operated on uneven ground. This repeated stress gradually altered the internal geometry of the housing. Even minute distortions affected how the bearings seated against their races. Once this alignment shifted, the bearings no longer rotated smoothly. Instead, they developed uneven contact patterns, increasing friction and accelerating wear. The damage compounded with every hour of operation, creating a cycle that could not be reversed by simple lubrication or adjustments. Farmers described several early warning signs. Some noticed faint vibration transmitted through the fenders during transport. Others observed grease leaking from seals that previously held tight. A few owners realized something was wrong only when metal particles appeared in the axle oil, an unmistakable sign that bearing failure was underway. Yet even when caught early, repair was complicated. Replacing the bearings did not solve the underlying issue if the housing itself had already begun to deform under stress. The consequences of ignoring the problem were severe. As the bearings deteriorated, the axle shafts lost stability. Under high load, this instability could cause additional stress on the differential, sometimes leading to chipped gears or accelerated wear in adjacent components. In rare but serious cases, operators experienced axle lockup or sudden loss of control, outcomes no farmer expected from a tractor carrying the John Deere name. Compounding the issue was the fact that the housing material, while strong, lacked the reinforcement necessary to distribute the 4020's torque evenly across its entire structure. Later engineering analyses showed that small reinforcements in critical areas could have prevented much of the deformation. But by the time these insights emerged, thousands of tractors were already in the field, experiencing the long-term effects of a flaw baked into their original design. The repair solutions varied. Some owners installed aftermarket heavy-duty bearings with improved load capacity. Others reinforced the housing with welding or structural inserts, although these modifications required significant skill and were not universally successful. John Deere eventually introduced updated components that helped mitigate the issue, but early production units continued to exhibit the defect even after repairs, simply because the original housing geometry had already changed. Among all of the mechanical weaknesses found in the 4020, the rear axle bearing defect carried a symbolic weight. It was a reminder that even the strongest-looking components could hide vulnerabilities invisible to the naked eye. The tractor's impressive power, one of its greatest selling points, contributed directly to the premature wear of the very parts expected to handle that power with confidence. For many farmers, discovering this flaw altered their understanding of the machine. The 4020 remained a respected tractor, but no longer an unquestioned one. Its successes in the field coexisted with a memory of bearings that wore too fast, housings that bent too easily, and repairs that cost far more than expected. The rear axle defect became a lasting chapter in its history, a chapter that demonstrated how even legendary tractors carry shadows behind their achievements.